Okay, we'll go ahead and get started. Can everyone hear me and see my screen?
Yes.
Thank you. So what I'd like to do today is I'd like to review the answers for the quiz number 4, and the answers are posted if you want to take a look at it later. And then we'll finish chapter 8. On Wednesday, we'll do chapter 9. And then I wanted to remind everyone that next Monday, the 23rd, we'll have exam number 4, and that will cover chapters 7 and 8. The other thing I wanted to mention is we do have one more quiz to take, and that will be a take-home quiz, and I'll put that out sometime next week, and I'll let you know about that. And that quiz will be on chapter 9. Okay, so for chapter 7, the quiz number 4, which covered chapter 7, the first question, calculate the effective nuclear charge for the outermost electron of aluminum. So to calculate effective nuclear charge, you want to take the atomic number. And so for aluminum, that's 13. And then you want to subtract the number of core electrons. And remember, we get the number of core electrons by going back to the nearest noble gas configuration. So in this case, that's 10 for neon. So those are the core electrons. So 13 minus 10. 13 minus 10 is 3. The second question is, once again, we're calculating that effective nuclear charge for aluminum, but this time we're using Slater's rules. So similar to before, you have the atomic number 13, and then in order to apply Slater's rules, you would want to go and look at the electron configuration for aluminum, and that's 1s2, 2s2, 2p6, 3s2, and 3p1. And then we would go ahead and apply those rules. So for the electrons that have the same principal quantum number as the outer shell, in this case that's 3, we would look at that. We have 3 of those electrons. We have 2 3s electrons and 1 3p electron. Since we're calculating it for that 3p electron, we don't count that one. So then it becomes that we have 2 electrons in that 3 level. So it's 0.35 times 2. Then we look at the n-1 level. So in this case, that's the principal quantum number 2. And we have 8 of those electrons, 2 2s electrons, and 6 2p electrons. And we apply that 0.85% factor to that. And then we have 2 electrons for that n-2 level. In this case, that's the 2 electrons in the 1s orbital. So we kind of add all those up to calculate our shielding constant for this using the Slater's rules, and we get subtract that from 13, and we get a value of 3.5. Number 3, oxides of most nonmetals combine with water to form, and the answer is an acid. Number 4, an increase in the effective nuclear charge causes the bonding radius to increase. That was false. It causes it to decrease rather. Number 5, in an isoelectronic series, ions have the same number of, the answer is electrons. Number 6, the first ionization energies of the elements blank as you go from left to right across a period of the periodic table, and blank as you go from bottom to top. of a group, and the answer was increase and increase. Number 7, which of the following species has the smallest ionic radius? That answer is aluminum +3. So with the +3 means you've removed electrons. And because it's a +3, it means you've removed 3 electrons, so that makes it even smaller. Number 8, 9, and 10, we're all writing balanced equations. I'll just say a couple things about getting points for these 3 questions. First of all, you had to write the equation going the correct way. So in other words, if you needed to have the reactants on the left, and the reactants are the things that are mentioned in the question, you had to have that on the left of the arrow and then over to whatever the product is. So if you had it flipped the other way, you did lose points. So you had to have that equation written correctly in terms of orientation. Then you also had to be able to write out the correct molecular or atomic formulas, and you had to balance the equation properly. So in other words, to get all 3 points, you had to do all those things. So the first one, reaction of cesium and chlorine gas, it's 2 cesium plus Cl2 going to 2 CsCl. Number 9, the reaction of selenium dioxide and aqueous potassium. So it was selenium dioxide, SeO2, plus 2 KOH going to K2SeO3 plus water. And then the last one, number 10, write the equation for the reaction of sodium and oxygen. So it's 4 Na plus O2, giving you 2 Na2O. Any questions about the quiz? Okay, I'm going to pull up the lecture and we will start the rest of chapter 8. So when we left off last week, we started to talk about covalent bonds. And one of the things we said about covalent bonds is that most bonds are covalent in nature. We had talked about ionic bonds before, but the reality is majority of bonds are covalent. And when we say a covalent bond, what we're talking about is atoms sharing electrons. So in the ionic bonds, you had one atom donating an electron and another atom picking it up. So you had a transfer of electrons. In covalent bonds, it's just sharing of electrons. So, and what we'll see today is that sometimes the sharing is equal, but a lot of times it isn't. And the things that influence that are, we have attraction of electrons and nuclei, we have repulsion of electrons, and we have repulsions between nuclei as well. And so for the bond to form, that attraction has to be greater than the repulsion. And the other thing we talked about is this electron density map down at the bottom, where we show that the electrons are in between the nuclei of the 2 atoms. And that area of where the electrons are more dense, that's where the bonding is occurring. In this representation, the electrons are kind of drawn equally across there. And what we'll see is that isn't always the case. And we have some terminology and some things that describe how that works. So one way we try and represent some of this bonding is through Lewis structures. So that's the dot structures that we started to talk about. and that we saw in one of our labs. And so when we are talking about sharing electrons to make covalent bonds, we draw these Lewis structures to represent that. And one of the things we typically do is we try and satisfy that octet rule so that we get to these kind of noble gas configurations. And so here's two examples below. So hydrogen, we know, has 1 electron in the valence shell. Chlorine has 6, or rather 7, because that's in the 7A group. And so we can draw the dots representing the electrons around to represent that. The other thing we have is we can also use this line to signify a single bond, and that means that we have 2 shared electrons. So either way is appropriate. When we're talking about covalent bonds, we usually are talking about nonmetals. So that's where the carbon, hydrogen, nitrogen, oxygen, things like that is usually what we're talking about when we talk about these covalence bonds. And remember that the group number, so is it 1A, 2A, 3A, 4A, 5A, 6A, 7A, that group tells us the number of valence electrons that that atom has. And so if something's in a 6A group, then we know that things like oxygen, sulfur, things like that, that has 6 valence electrons because it's in that 6A group. So what we're trying to do is then form that octet and form the simplest molecule for these nonmetals to complete the octet. The one exception to that is hydrogen, because hydrogen only has the 1 electron. We don't worry about getting an octet for that, but for all the others we do. And so here are some examples of what that would look like. So we look at the first example, HF, and fluorine's in the 7A group. So it would start with 7 electrons, so 7 dots around it. Hydrogen is in that 1A group. It has 1 dot around it, 1 electron. So the line between hydrogen and fluorine, that indicates 2 electrons make up that line, which is the bond. And so the hydrogen and the fluorine are sharing those 2 electrons. The other 6 electrons around the fluorine, those are just on the fluorine. Those aren't shared. We go to the next example, which is water. And once again, we can start by knowing that oxygen has 6 valence electrons. We know that because it's in the 6A group. So we have 2 pairs of free electrons, of lone electrons. That's the 4 dots that you see. And then we have shared electrons for the OH-2OH bonds. So once again, that satisfies our octet for the oxygen. Then we move on to the ammonia, NH3. The nitrogen's in the 5A group. So we know there are 5 valence electrons for that. So we have 1 electron being shared with the 1 electron from hydrogen for each of those NH bonds. So there's 3 of our valence electrons for nitrogen taken up in those NH bonds. And that leaves us with 1 pair of free electrons on the nitrogen to complete its octet. And finally, the last example is methane. And we know from the periodic table that carbon's in the 4A group. And so that tells us we have 4 electrons, 4 valence electrons. And in this case, we have shared electrons between carbon and hydrogen. So sharing that carbon electron and electron from the hydrogen gives us 4 single bonds around the carbon. So these are examples of completing that octet. So in other words, completing 8 electrons around the central atom, and then that may be done either through bonding and sharing electrons with another atom, or it can be a combination of bonding and free electrons that are just on that central atom. And the key to that is using the periodic table to see how many valence electrons are on the atoms. So as we said on this previous slide, we had examples of on fluorine, oxygen, and nitrogen, where we have some dots representing electrons that aren't associated with the bond. Those are called free electrons or lone pairs of electrons. And they are only on that atom. They're not being shared. They're only on the atom that they're associated with. The other electrons, the ones in this case that are between the H and the F, or the H and the O, H and N, and H and C, those are called bonding electrons, so bonding pairs. And so these are shared electrons in that Lewis structure, and that's what it's designating. And we, as we said, we can have those as either two dots or one line, but you don't want to put both on there. So it's more common for the bonds to have the line there than to have the dots. Because if you start doing all the dots, it gets a little confusing sometimes. The dots are usually reserved for free electrons, and then the bonding electrons, it's more common to draw the line. We saw this in the lab, that we had some examples of multiple bonds. So when you share one pair of electrons, we call those bonds single bonds. If you share two pairs of electrons, then that would be double bonds. And then sharing three pairs of electrons would be triple bonds. And so here we have an example of double bonds and triple bonds. And so for the first one, the double bond example, we see we have 6 valence electrons around the oxygen atoms. And once again, we know that because it's the 6A group. And then we have 4 valence electrons around carbon, and that's because it's in the 4A group. And what we see is that in order to get the octet, so in other words, 8 electrons around the carbon and the oxygen both, one way of doing that is by having double bonds between the carbon and the oxygens. So if you count up those electrons around the carbon and around the oxygen, then in each case you can satisfy the octet rule by sharing electrons in those double bonds. Similar idea with the N2 below it, the 2 nitrogens. So nitrogen is a 5A group element. So we have 5 valence electrons around that. And the only way to satisfy the octet for that is to have a triple bond between the 3. So we have 6 electrons being shared between the 2 nitrogen atoms, and then each one has 2 lone pairs, 2 lone pair electrons on it. So that satisfies our octet there. So sometimes you can satisfy the octet by having single bonds all around, as we saw in the first examples. Then on these, we see examples of where you need to have either a double or triple bond. Double bonds are fairly common, triple are a little less common, but sometimes you need that in order to satisfy the octet rule. So we said that in a covalent bond, we're sharing electrons between the atoms. The reality is that sometimes that sharing is equal, but other times it's not. So the electrons will be shifted a little bit more towards one of the atoms versus the other. And so there's some terminology that we have which help us understand that and explain that. And polarity is one term that you'll hear. Bond polarity is simply a measure of how equally or unequally those electrons in the covalent bond are shared. So if it's shared equally, we say that's nonpolar. If it's not shared equally, then we say it's polar. And so once again, polarity is a term that we use when talking about covalent bonds to describe how the electrons are being shared. If they're being shared equally, we say it's a nonpolar covalent bond. If the sharing is not equal, then we say it's a polar covalent bond. And this concept of polar and nonpolar, it applies to individual bonds. It also applies to molecules themselves. And this idea of polarity versus nonpolarity and compounds being polar or bonds being polar or nonpolar is really central in understanding how a lot of chemistry reactions occur and how some physical properties occur as well. So we'll talk a little bit more about this. In the world of like reaction chemistry and in a lot of areas of chemistry, polarity is a really big deal. So here's an example of some fluorine compounds. And so for F2, elemental fluorine, we see that down at the bottom, there's some color-coded diagrams. And so the blue color means low electron density, the red color means high electron density. We see on F2 that it's kind of in the middle. It's kind of that greenish yellow. And so what that's saying is that one fluorine atom versus the other, the electron density isn't higher on one versus the other. So since it's equal across that covalent bond, that tells us that it's a nonpolar bond. So remember, nonpolar means the electrons don't favor one atom over another. When we look at HF, the next one, we see that there's some red over on the fluorine atom. And so that's telling us that the electron density is higher over there than it is on the hydrogen. Because that electron density is higher over there, you'll have a partial negative charge over there and a partial positive charge on the other side because the electrons have kind of shifted away from the hydrogen. And then finally, lithium fluoride, we see even a stronger pull of the electrons over towards the fluorine atom. And we see a lot of red over on the right-hand side with the fluorine, and then a lot of blue on the left-hand side with the lithium. So that's telling us in this covalent bond, the electrons, while they're being shared, they're more tilted towards that fluorine side. And this gets down to what the definition of polarity is that shifting of electrons, even though they're being shared, so it hasn't been donated, it's still shared, but it's not an equal sharing of the electrons. One way that we express this ability to draw electrons towards a particular element is the concept of electronegativity. So electronegativity is a really key thing in understanding polarity and understanding polar molecules and polar bonds and nonpolar and things like that. So this version of the periodic table that you see in this plot here, is really important. So if you're going to learn one thing in this chapter, this is a real important thing to learn. So in general, electronegativity is the ability of that atom in a molecule to attract electrons to itself. So in other words, going back here, if we were to go back here, we would say that in lithium fluoride, for instance, that ability for fluorine to attract those electrons, we would suspect that it's probably pretty electronegative. And sure enough, if we look at our table here, we see by the color coding that the ones in red are the most electronegative. So in other words, the elements in red, nitrogen, oxygen, fluorine, chlorine, those elements are the ones that have the greatest ability to pull electrons to themselves when they're in a molecule. In general, as you go from left to right, electronegativity increases. And when you go from bottom to top, electronegativity increases. So the electronegativity is the greatest in that upper right-hand corner of the periodic table. And we see by looking at the electronegativity values in that table that fluorine is the highest value followed by oxygen, nitrogen, and chlorine. So if those elements are involved in a bond, they're going to pull the electrons towards them. And so that's really important. That's the other thing that's going to tell us is that if you have nitrogen, oxygen, fluorine, chlorine, if those are in your molecule, you most likely are going to have a polar molecule. If you think of something that's nonpolar, it would be, think back to when we talked about alkanes. Remember, alkanes were carbon and hydrogen containing compounds. Well, those don't have much polarity because if we look at our carbon and hydrogen values, they're pretty similar, 2.1, 2.5, not a big difference there. So you don't have a lot of shifting of that sharing of electrons with that. Now you start adding nitrogen in, oxygen, fluorine, chlorine, those things. Then you start getting a little bit bigger difference on these things, and you start seeing some movement of those electrons in terms of how they're shared. So taking into account that electronegativity and how those values impact how the electrons are shared in that covalent bond, we'll call some covalent bonds polar. So we'll call bonds polar, we'll call the whole compound polar or nonpolar, kind of depending upon how these electrons are shared. So we represent this in a way that reflects that the electrons are going to spend more time around that electronegative atom. And at the bottom, there's two ways that people express this. And so with the HF example, so fluorine we know is very electronegative. That was upper right-hand corner on our table, just looking at that again. So the fluorine is up there in the upper right-hand corner. So we know that fluorine is more electronegative than hydrogen. So in that bond, that covalent bond between the hydrogen and fluorine atoms, we know the electrons are going to be pulled over towards the fluorine atom. And so you can represent that two ways. One way is with the delta negative sign over the fluorine, delta positive over the hydrogen. Or, and to be honest, this next way is the more common way to do it, is you have the arrow, and the arrow goes towards the more electronegative, and then you have like a little plus on the end of the arrow representing the side that has less of the electron shifted their way. So this second one with the HF and the little plus over the hydrogen and then the arrow pointing towards the fluorine, that's probably the more common way of showing that you have that unequal sharing of electrons. And in this case, more of the electrons are over on the fluorine than the hydrogen. So when we talk about these polar covalent bonds, this is based on that difference in electronegativity. And so that greater the difference in electronegativity, the more polar is the bond. And so here's some examples of as you go down that 7A group, so fluorine down to iodine, and we see, because we know fluorine's the most electronegative and that decreases as you go down the column, we see some trends. We see, first of all, we see electronegativity difference and dipole moment. And we see those decreasing as we go down, and that's what we would expect. The picture on the bottom, I think, really is a nice color coding of it, where once again, the negative is red and the blue is positive. And we see the colors changing. So for HF, you see a lot of electron probability over towards the fluorine. And by the time you get to HI, it's kind of evened out a little bit. We also see, which is interesting, as the more electronegative situation you have, so the more polar situation you have a shorter bond length. So it starts at 0.092 for the HF and winds up at 1.61 for HI. So you have a bond length difference as well. So when we have two equal but opposite charges that are separated by a distance, we say something called a dipole forms. And so by the equal but opposite charges, that simply means that it's a plus and a minus, or a +2 and a -2, or something like that. There's not like a plus and a -2, or a +2 and a -1, or something like that. You can calculate something called a dipole moment to kind of get to have a quantitative number, and that goes back to the charge and then that distance that the opposite charges are separated. So far we've been talking about polar bonds. There's also polar molecules, which coincides with the polar bonds. So we talk about polar bonds, we talk about entire molecules being polar or non-polar, but it's the same concept in either case. Just as with you're looking at bonds to see if one atom is more electronegative than the other, that'll shift the bond. You start looking at areas of the molecule to see if there are areas of the molecule that you would have electrons shifting over to one atom versus the other. If you have a lot of those kind of things, then that's a more polar molecule. If you have less, it's less polar or non-polar. Polarity helps determine some of the chemical properties that we observe. Polar molecules themselves will align with their positive end to a negative end, and the negative end will align if there are ions around to a positive ion, and the positive end will align if there are ions around in a negative ion. So when we talk about these things, we're usually talking about something going on in solutions. The other one that is pretty common when you think of polarity is if you've ever heard the phrase like dissolves like. So polar compounds dissolve polar compounds, non-polar compounds dissolve non-polar compounds. And so one example of that is if you've ever used like a frying pan to cook something and then the grease hardens on the pan. If you simply try and wash it off with water, it doesn't work. And the reason for that is that grease is very non-polar. The water molecule is a very polar molecule. And this goes back to the like dissolves like. So you need something that is non-polar to dissolve that non-polar grease. And that's where adding a soap or detergent or something with a non-polar functional group on it will help dissolve and loosen up the grease. Pretty much all the cleaning type things that are done, whether you're talking about washing your clothes or washing dishes or cleaning the bathroom or any of that stuff, that gets down to solubility, and a lot of that centers around this like dissolves like. And depending upon what it is you're trying to dissolve, making sure that the cleaning agent is the same polarity is a big deal. So polarity is big on just what I would call day-to-day living stuff, and it's also big on chemical reactions of understanding those. So if you're trying to decide if a compound is ionic or covalent, we've talked about that if it's a metal plus a non-metal, that's usually an ionic compound. So remember, we talked about how metals like to donate electrons, non-metals like to receive or pick up electrons. And so we had examples of that in the past of where those metals donate electrons to the non-metals. And so then you have an ionic compound. So that's a case where there's actually electron donation. So electron donation going on. When we talk non-metal plus non-metal, which is usually what we define as a covalent bond, there, remember, we're sharing electrons, we're not donating. Now, as we've just learned, that sharing may not be equal. And if it's not equal, then we have the concept of polarity and electronegativity and all that stuff to take into account. but it still is a sharing. So as usual, there are exceptions. And so if we have a metal with a high oxidation number, then we can't have instances of covalent bonding there. So there are some times when metals do form covalent bonds, and that goes back to the oxidation number issue. We can use electronegativity differences to try and understand some of this, but it doesn't take into account that oxidation number issue. So now I'd like to take a little bit of time to talk about writing Lewis structures. So that's the dot structures for covalent molecules. So the way we go about doing this is we sum up the valence electrons for all the atoms, and then we take into account the overall charge. And by overall charge, we're saying if the molecule itself is an ion. If it's an anion, then we add the number of electrons to represent what the negative charge is. So if it's a -1 charge, we'd add 1 additional electron. If it's -2, we'd add 2 additional electrons. If it's a cation, then we have to take away 1 electron for every positive charge. So in that instance, if it's +1, we would remove 1 electron from the total. If it was +2, we'd remove 2 electrons from the total. So, but to start with, we would look at the atoms. So let's look at this example of PCl3. So for phosphorus is a 5A element. So that tells us we have 5 valence electrons associated with it. So that's where the 5 comes from. We have 3 chlorine atoms in this example, and chlorine is a 7A element. So we have 7 valence electrons for each of those. So we have 3 times 7 to represent chlorine valence electrons. So that gives us a total of 26 electrons that we have to work with. We said before that those shared electrons and the bonding electrons, we can represent by putting the dots in, but it's probably a little easier to draw a line between the atoms. And that line represents 2 shared electrons. So let's go ahead and start by putting phosphorus as our central atom and then attaching the 3 chlorine atoms to it. So as I said, those bonding lines each represent 2 electrons. So if we add that up, we have 3 of those. So 2 times 3 would be 6. So from our total of 26 electrons, let's subtract 6 electrons after doing the bonding, and let's allocate those 20 electrons that we have left. The next thing we want to do is we want to complete the octets for each of the atoms that bonds to our central atom. In this case, it's the chlorine. So the chlorine has 2 shared electrons there, as signified by that bond with the fluorine. So we need to add 6 more electrons to each chlorine atom to give us 8 total. So that's the 6 dots you see around each of those chlorine atoms. So we've added 6 to each of 3, that's a total of 18. And so let's subtract that 18 from our 20. Remember, we started with 26. We had 6 bonding electrons. That got us to 20. Now we have 18 electrons that are not involved in bonding around the chlorines. That leaves us with 2 electrons still to do something with. Well, we then can place those remaining electrons on that central atom. So that's the 2 dots that you see on the fluorine. And let's go ahead and let's count all of these atoms to see if we have the octet rule satisfied for each of them. So the chlorines have 6 free electrons and then 2 electrons that they're sharing with the phosphorus. So we have 8 electrons around each of those. So we satisfied the octet rule for them. For the phosphorus, we have 3 three bonds where we're sharing with chlorine. So that's a total of 6 bonding electrons that we're sharing. And then we have the 2 free electrons as well. So that is our total of 8 electrons around the phosphorus. So we're good there too. We have satisfied the octet rule for phosphorus and also each of the chlorine atoms. Sometimes when you do this exercise, you may not have enough electrons around that central atom. If that's the case, if you've used all your electrons up and you're not able to satisfy the octet rule, you may need to do multiple bonds. So in other words, a double bond or a triple bond between that central atom and one of the other atoms. This case, it worked out, we didn't have to do that, but that's what we would do if we didn't get the octet for the phosphorus in this case. Let's take a look at some examples of what you would do in this case. So for HCN, hydrogen cyanide, we have carbon as our central atom. So because carbon is a 4A element, we know that we would be starting with 4 electrons there. And so right now, if we just drew it with a single bond from carbon to hydrogen, and then a single bond from carbon to nitrogen, and then had 6 electrons around that, free electrons around that nitrogen, we'd satisfy the octet for nitrogen, we'd have 8 there, but we only have 4 electrons around the carbon. So we need to pick up 4 more electrons. Well, one way we can do that is by taking 2 of those lone pairs from the nitrogen, and instead of having a single bond between carbon and nitrogen, we have a triple bond between carbon and nitrogen. So now if we go back and count electrons around these elements, we see carbon has 1 shared pair with hydrogen and 3 shared paired with nitrogen. So for a total of 8 shared electrons. The nitrogen has 3 pairs shared with carbon and then 1 lone pair. So once again, we have 8 around the nitrogen. So by making this bond between carbon and nitrogen a triple bond rather than a single bond, we now have satisfied the octet rule for both nitrogen and carbon. Another thing that comes up is we can draw a structure more than one way, and yet they both satisfy the octet rule. And so down at the bottom of this slide, we see CO2, and we see it drawn 2 ways. One, where carbon has a double bond to each of the oxygen atoms, and the other option is carbon with a single bond to one oxygen and a triple bond to the other oxygen. So if we go and look at this carefully and check our octet rule, we see that everything is okay in each of these. So then it becomes, well, which one is the correct way to draw it? Is the C with the double bond oxygen, double bond oxygen? Is that the correct one? Or is it the carbon with a single bonded oxygen and a triple bonded oxygen? Well, in order to figure this out, there's something called formal charge that can be calculated. And the formal charge is the charge an atom would have if all the electrons in a covalent bond were shared equally. And so the way you calculate that is you have the number of valence electrons. And remember, we get the number of valence electrons from what group it is in the periodic table. And then from that, we subtract 1/2 times the bonding electrons, and then subtract all the non-bonding electrons. So that's those free dots that you see that aren't involved in a bond. So let's go ahead and do that for these 2 that we're considering down at the bottom. So we talk about valence electrons, and we look at oxygen, and that's in the 6A group. So because it's in the 6A group, we know there's 6 valence electrons. For carbon, we look at that where it's at in the periodic table, and that's in the 4A group. So that tells us there's 4 valence electrons there. So we go ahead and list out our valence electrons. Remember, we said to calculate this formal charge, we're going to have the number of valence electrons, which we just did, minus half the bonding electrons and minus half the non-bonding, and minus half the bonding electrons and minus all the non-bonding electrons. So now the way this is written on the first one with this 2 oxygens double bonded to the carbon, if we look at the electrons around that atom, we have 2 bonding electrons. We have 4 bonding electrons, 2 for each bond. And so we do 1/2 times 4, so that's 2. And then we have 4 non-bonding electrons. So that's the dots that we see. So we have a total of 6, is if we add those 2 up. So that's the electrons assigned to the atom. That's the sum of 1/2 the bonding electrons and all the non-bonding electrons. So we go ahead and do that for oxygen. We can do that for carbon. Carbon, we have 8 bonding electrons. 8 divided by 2 is 4. So if we go ahead and then subtract those electrons that are assigned to the individual atoms from the valence electrons, for the CO, where each of the O's are double bonded to the carbon, we see the formal charge is 0 across the board. If we look at the second option, we look at the oxygen first there, we can go ahead and do that. The valence electrons are going to stay the same because that's just based on what element it is. But the electrons assigned to the atom for the first oxygen, the single bonded oxygen, well, we have 2 electrons that are involved in bonding. So 1/2 times 2 is 1. And then we have 6 free electrons. That's the non-bonding ones, the dots that we see. We have 6 of those. So 6 plus 1 is 7. So we have 7 electrons assigned to that atom. The carbon, we have 8 bonding electrons. So that's 4 again, just as it was in the first example. And then the last oxygen, we have 6 bonding electrons. So 1/2 times 6 is 3. And then we add the 2 non-bonding, the 2 free electrons for a total of 5. So if we do that math, we see the first oxygen is -1, the carbon's 0 again, and the second oxygen, the triple bonded oxygen, has a value of 5 for its electrons assigned, so its formal charge is +1. So we have one choice where the formal charges are all 0. We have a second choice where we have formal charges of -1, 0, and +1. Well, one of the rules is that the dominant Lewis structure is the one in which the atoms have formal charges closest to 0. So we go back here and look at this, and we see we have one option where the formal charges is 0, 0, 0, versus an option where the formal charge is -1, 0, and +1. So this guidance that we get here is that the dominant Lewis structure is the one in which atoms have formal charges closest to 0, tells us that the CO with the double bonds to for each of the CO bonds is the one that is the more dominant structure, the more likely structure, because there we have 0s across the board for formal charge versus what we have on the second choice. Well, this one works out pretty clean where you get 0s across the board, but it doesn't always work that way. And so a second guide that we have is whichever configuration gives us negative formal charge on the most electronegative atom, that is favored. So let's look at this example below to see how that helps us. So we could go through that same exercise as we did So remember here, we looked at the number of valence electrons. We totaled up the bond, 1/2 times the bonding electrons and then the non-bonding electrons. We did that subtraction to get our formal charge. So we could go ahead and do a similar exercise here with the nitrogen, carbon, and sulfur. The one thing to remember on this example, though, is notice that this is an ion. And so there's a negative charge associated with it. So in addition to those electrons, we have an extra electron that is because it's an anion. But if we went and calculated out our formal charges, we would find on the left one, it's -2, 0, +1. The middle option, -1, 0, 0. The option on the right-hand side, 0, 0, 1. So the first thing we do is we look over on that left-handed option, and we see for that Lewis structure, we're not as close to 0 formal charge as we are with these other two, because we've got a -2, we've got a +1, we've got a 0. The other two options have 2 zeros on 2 of the atoms, have zeros on 2 of the atoms, and then -1 on the third atom. So in terms of which one has atoms with the formal charges closest to 0, there's really no difference between the middle and right-hand options. So that's where it comes to the second rule that we had of we want a negative formal charge on the most electronegative atom. So what this would force us to do is to go back and look at that table and remember that table of electronegativity that we talked about. And remember, we said that upper right-hand corner, that's the most electronegative. And if we were to go back to that and look at it, we would see that nitrogen is more electronegative than sulfur. And so what that means is the Lewis structure that's favored would be the one that would have nitrogen with a negative formal charge. And that's the choice in the middle. So that choice in the middle where we have carbon with a double bond to the nitrogen and carbon with a double bond to the sulfur, that results in a lot of formal charges around 0. And also for the ones that aren't 0, it gives us a negative formal charge on the most electronegative atom in this molecule. So we talked a little bit about rules to figure out what the best Lewis structure is. So let's talk about that a little bit more, because the formal charge rules are nice, but sometimes there's something where, based on the limitations we have in how we draw these Lewis structures, it's not really possible to draw a Lewis structure that totally explains everything. Here in this case, we're talking about ozone, O3, and we have 2 structures here. If we look on the right-hand side, we have 2 Lewis dot structures where we have oxygen double bonded to oxygen, then that oxygen with a single bond to the other oxygen, and then we have the flip of doing it the other way. And so if you actually look at an electron density distribution of this, it's really pretty symmetrical. So you would expect with a double bond on one side and a single bond on the other that it would not be symmetrical. This just indicates that neither of those Lewis structures is actually totally correct. It's somewhere in between. In the lab, you saw an example of this with the benzene molecule and had some questions about this. And this leads us to what we call resonance structures. So this resonance structure just means that there's more, that you need to draw more than one Lewis dot structure to truly represent what it looks like. And here's that benzene example that I mentioned we saw in the lab. You see structures drawn above for benzene, each of them are alternating double and single bonds, but you see they're slightly different in terms of the orientation. And so the reality is neither one of these is actually correct. For benzene, it really isn't an alternating double and single bond. And that's why often you see over here on the right-hand side, the 6-member ring drawn with a circle in the middle. And the circle is really a better representation than the alternating double and single bonds, because the electrons are actually shared by more than just the two atoms. When we talk about sharing electrons, usually we're talking about the two atoms involved in the bond sharing electrons, and that's called localized electrons. There's also something called delocalization, and so delocalization involves electrons that are shared across multiple atoms, and that's really what you have going on in benzene. You have these electrons that don't just share between the two carbon atoms next to them. It's more of a group sharing with all the carbon atoms in the ring, and that results in a more equal distribution of the electrons throughout that carbon circle, that carbon chain. And so those electrons are called delocalized. So the octet rule works fairly well. There are exceptions to that, and we'd like to go over a couple of those exceptions. One is you can have ions or molecules with an odd number of electrons. Another one is sometimes you have less than an octet, and then other times you have more than an octet. And so when you have more than those 8 valence electrons, that's called an expanded octet. So let's talk about those for a few moments. The odd electron one, here's an example of it. And we're not going to really spend any time on that because, in all honesty, you don't find these very often. They tend to be unstable, very reactive, and so we're not going to worry about that. The fewer than 8 electrons, that happens. That's not uncommon to see that. Boron and beryllium are 2 examples of this that can make stable compounds with fewer than 8 electrons. And let's take a look at an example, a boron example, BF3. BF3 is actually a fairly common reagent that's used. And if you look down at the bottom, there's 4 different ways that you could represent the Lewis structure for BF3. So over on the left is boron with 3 fluorine atoms attached. And you'll notice there, boron is not satisfying the octet rule. It has 6 electrons around it, so 3 shared pairs with the fluorine in the bond, BF bonds. But we don't have any free electrons or any double bonds or anything there, so the boron does not reach an octet. On the right-hand side, we see boron with a double bond to one of the 3 different fluorines. So in that case, you might think that that's the better structure because we've satisfied the octet for the boron and we've satisfied the octet for the fluorine. The problem with it is if we look at the charges placed, giving that boron an octet gives you a negative charge on the boron and a positive charge on the fluorine. So if we go back and we look at, we talked about here of looking at formal charge type stuff. If we look at it in that vein, then we see that, well, positive for fluorine, negative for boron. It solves one problem in terms of getting the octet rule satisfied, but that's not really what happens. We know from that periodic table graph of electronegativity that fluorine is the most electronegative element in the whole periodic table. So it's kind of hard to believe that a stable molecule would have fluorine with any type of positive charge associated with it. So so because of that, of just understanding really what, in this case, that fluorine is an atom that really likes to attract electrons, that the idea of it giving up electrons in a bonding situation is pretty difficult for that to be a reality. So here, by filling that octet, we would force these atoms, and like I said here, one of the keys is fluorine, to go against what its normal tendencies are. So that's the reason why in this case, it's better to have not fill that octet, even though that's what we normally are striving for, because of that electronegativity of this case in the fluorine atom. Sometimes we get more than 8 electrons, and we had one example of that in the lab. And so that's called hypervalent. And here's an example of phosphorus with 5 fluorines around it. So what I'd like to do now is just go over a couple of homework problems, and the rest you can do as you practice. But I'd like to go over a couple just to make sure that we're on the same page on this. So let's look at 8.33. So in 8.33, we're talking about writing the Lewis structures and symbols for silicon tetrachloride. So we would start by saying, how do we represent silicon? Well, we would look up on our periodic table to see what column it is, what group it is, and we see that it's in silicon's in the 4A group. So we would have the symbol for the element silicon, and then we'd put 4 dots around it to represent those 4 valence electrons. Then we would look up chlorine. Chlorine is in the 7A group. And so that tells us that we have 7 valence electrons there. And so we would draw the 7 electrons around the chlorine, and to do silicon tetrachloride, we would then combine those. So we would want to make it so that we had silicon, which is the central atom in this. We have the 4 bonding electrons around that with the chlorine. Then we would we'd have the free electrons around each chlorine atom, and by drawing it with silicon with 4 chlorines, and then make sure when you do something like this that you put in all the electrons or free electrons around the chlorine. So we have the line signifying single bonds, which designate that we're sharing electrons between the silicon and the chlorine, and then we'd have the free electrons there. Let's look at 8.41. So we're being asked, are these bonds polar or not? Remember, we say a bond is polar if there's an electronegativity difference between the 2 atoms. So in the first one, BF, we know fluorine is the most electronegative element. We know that from that, once again, that upper right-hand corner in that electronegativity table telling us that. And the way we draw that is we have the arrow pointing towards the more electronegative element, and then the little plus end being the less electronegative. Of these, the only one that is not polar is the ClCl. So the chlorine one, and that's the case of where if you ever have 2 of the same element, that by definition is nonpolar because it's the same atom same element rather. So you're not going to have one atom be more polar than the other or more electronegative than the other. We see the same thing with the selenium and the oxygen, the hydrogen and the iodine, where we use that electronegativity table to pick out which element is more electronegative. Remembering in the upper right-hand corner, those are the more electronegative elements. And then we draw it so the arrow goes towards that element, and then the little plus sign is on the one that's less electronegative. Okay, 8.47. In 8.47, we're talking about drawing some Lewis structures. Once again, we would start with getting that central atom, in this case silicon, and looking up where it is in the periodic table. It's a 4A, so we would put 4 dots around it. Then we know each of those hydrogens has 1 valence electron, and we would combine that with to share and create a bond with each of the silicon electrons. And then we would wind up with silicon with the 4 hydrogens attached. CO, in that case, we look at carbon. Carbon's a 4A element, so we'd have 4 valence electrons there. Oxygen, a 6A element, so we have 6 electrons around that. And what we see there is, in order to get the octet rule satisfied for carbon and oxygen, we have to do a triple bond in between those. The next one, SF2, I actually drew the wrong structure. Sulfur, if we look up sulfur, we see that's a 6A element. And so we would have 6 valence electrons around that. Fluorine is a 7A, so there's 7 valence electrons there. So if we do a single bond from sulfur to fluorine, and we have 2 of those single bonds, then we would have that, and then we would have 2 lone pairs around the sulfur. So ignore those other 2 fluorines that for some weird reason I put on there, and just put lone pairs on those spots. Sulfuric acid, H2SO4, and they tell us that the hydrogen is bonded to an oxygen. So in other words, it's an OH group. So in that case, we start with the sulfur, and once again, sulfur has 6 valence electrons, so we'd put those 6 electrons in. Then we would start the sharing with the oxygens, and then we would start the sharings with the oxygens that are part of the OH. And so what that would give us is the sulfur bonded to, single bonded to 2 oxygens and then to 2 OHs for that Lewis structure. The ClO2 would be a similar idea, where you would have 7 valence electrons around the chlorine, 6 valence electrons around each oxygen. Because it is a -1 charged ion, we have an extra electron we get to add to the group in order to fill things out. And then finally, the last one, NH2OH, the nitrogen, we look that up. It's a 5A element. So there's 5 valence electrons there. So we have 3 electrons that are taking part in bonding, 2 with hydrogen atoms and 1 with an OH group. And then finally, we have 2 lone pair electrons on that nitrogen. So practice doing Lewis structures so that you get comfortable doing those. In 8.51, they're asking us, once again, to write the Lewis structure and then assign oxidation numbers and formal charges. So we can start by looking up oxygen, carbon, and sulfur on the periodic table. And we see that oxygen has 6 electrons, valence electrons, carbon has 4, sulfur has 6 as well. So we have 16 total valence electrons. And so we can use that information to put together our Lewis structure, which is oxygen double bonded to carbon, and then the carbon also double bonded to sulfur. We can calculate out the formal charge of this. So we have those number of valence electrons minus 1/2 times the number of bonding electrons minus the number of free electrons. So in our molecule here, we look at the oxygen, so we know that there's 6 valence electrons there. We have 4 bonding electrons, and then we also have 4 free electrons. So if we do that math, we see the formal charge there is 0. For carbon, we have 4 valence electrons. We have 8 bonding electrons, half of that 8, so that's a 0 there. And then a 0 also for the sulfur if we go ahead and do that. So the fact that our formal charge is 0 across the board tells us that we're pretty good in terms of this being a reasonable Lewis structure. Oxidation numbers, we can figure that out from the periodic table. We know from the past that oxygen likes to be -2 for an oxidation number. Same with sulfur. If those two are -2 and our molecule is neutrally charged, then that tells us that our carbon needs to be +4. Let's talk about bond enthalpies just for a minute. This will wrap things up. So bond enthalpy, remember enthalpy is delta H. Bond enthalpies are positive, and that's because you have to put energy into a bond to break it. So it's an endothermic process. And the higher the number, the stronger the bond. So here are just some common bond enthalpy values. But what I really want to get to is this part here. And we saw some of this in the lab. Multiple bonds are stronger than single bonds. So triple and double bonds are stronger than a single bond. We can also look at what the bond lengths are for these types of bonds. And in general, as the number of bonds between 2 atoms increases, the bonds become stronger and shorter. And I believe you saw that in the lab, that triple bond length was shorter than double, double was shorter than single. And so the thing to remember here is, as the number of bonds between 2 atoms increases, the bond becomes shorter and stronger. So that's the takeaway I want you to have on this part. There is a way to do some delta H calculations based on the bond energies. And so I'm just going to briefly go over that. So you would use those numbers that are in a bond energy table. But basically what you're doing is you're looking at the molecule. And in this example, the molecule is drawn out so you can see how the bonding is. And you're counting the bonds. So for instance, on that first molecule, ethane, on the left-hand side, on the reactant side, you have 4 carbon-hydrogen bonds. So you'd have 4 times the enthalpy of those bonds. Then you have 1 carbon-carbon double bond. So you'd have 1 times that enthalpy. The next compound, you have 2 OH bonds, and you have 1 OO bond. So you look up the enthalpies for that. So that's what the numbers, the 413, 614 on down the line are there. Those are just the values you would look up. Then you subtract from that the formation enthalpy values for those bonds. And so it's negative because remember we said putting energy in to break the bond, so it's going to be exothermic for the bond being formed. So in that case, you would go and you would look and you would say, okay, how many OH bonds do I have? I have 2 of those. How many CO bonds do I have? I have 2 of those. How many CH bonds do I have? I have 4 of those. And then how many CC bonds do I have? I have one of those. So you'd work out those coefficients based on the number of bonds that you see in the molecule. And then you would look up in the table what the bond energy was, and then do the math for that. So these types of bond energies, as long as you recognize where the bonds are, I think they're straightforward. And so that is where we're going to end for today. Just a reminder, Wednesday we'll cover chapter 9, and then next Monday will be an exam on chapters 7 and 8. Any questions? Okay, thank you.